Lecture 10 covers sections 4.3 through 4.4. At the end of today's lecture, you should be able to calculate the center of area of a composite body using our tabulated values. You should also be able to determine the resultant and the subsequent point of application for 2- and 3-dimensional distributed loads via methods of integration, as well as using our tabulated values for centroids. For us to begin, let us talk about centroids of composites. Recall our first moment of areas are given as follows. X bar is equal to 1 per area times the integral of x dA. The same follows for y bar and z bar. However, we just replace x with y and z respectively. Now, recall x bar, y bar, and z bar give us the location to our center of area in reference to our defined origin. Now, in a situation where we have a composite, we can calculate the centroid of said composite by summing or subtracting our base shapes. For instance, if we look at the figure to the left, we have a very unique shape where we're trying to determine our center of area, x bar and y bar. To do this, we can break the shape down into 3 basic components: 2 triangles, A1 and A2, and a square, A3. To determine x bar, all we have to do is sum the moments due to each of our unique areas per the total area of our system. That is, x bar would be x bar 1, A1, plus x bar 2, A2, plus x bar 3, A3, divided by the sum of A1, A2, and A3. Likewise, we can do this for y bar. Y bar would be equal to y bar 1, A1, plus y bar 2, A2, plus y bar 3, A3, per A1 plus A2 plus A3. Now, what's nice about this is we know x bar 1 and y bar 1 of our triangle. It's just 1/3 of base and 1/3 of height measured from the heavy side. And we know the area, 1/2 base times height. Using principal shapes, we can easily populate now our equation to calculate the centroid of a composite body. Let us look at an example. For the shapes shown below, we want to determine the location of the centroid and their first moments of area, MYZ and MZX. Now in this shape, we notice we have a few principal shapes that we can build it upon. That is, we can decompose this as a rectangle that has a width of 120 millimeters and a height of 80 millimeters, plus a triangle that has a width of 120 millimeters and a height of 60 millimeters, plus a hemisphere that has a radius of 60 millimeters, minus a circle that has a diameter of 80 millimeters. Now, we can calculate the areas of each of these shapes and their x bar and y bar locations. And then we will use this in our total centroid equation. And thus, if we define this in relation to our origin, we can find the centroid of our composite body. For us to begin, let us look at a rectangle. A rectangle had a height of 80 millimeters and a width of 120 millimeters. That is, our area is 120 millimeters times 80 millimeters, which gives us 9,600 millimeters squared. The centroid of a rectangle is quite simple. It's our width divided by 2 and our height divided by 2 for x bar and y bar. Thus, our x bar is equal to 60.0 millimeters and our y bar is equal to 40.0 millimeters. Now for the triangle, note that this exists below our x-axis. Our area in this situation is positive, where we have 1/2 our base times our height, i.e. 1/2 of 120 millimeters times 60 millimeters, which gives us 3,600. But now our x bar and y bar, which is 1/3 our base and 1/3 our height, is going to be expressed as 40 millimeters and minus 20 millimeters. Notice our y bar is existing below the x-axis, and it'll have a minus sign associated with it. Now the area of a hemisphere is pi r squared divided by 2. The radius is 60 millimeters, and thus we have an area of 5,660 millimeters squared. Now, we note that the centroid of a hemisphere is 4r divided by 3 pi. Now, this would give us 25.5 millimeters. And we have to add this to our height, i.e. that our hemisphere is 80 millimeters starting above our x-axis. Thus, our y bar location would be 105.5 millimeters, whereas our x bar is just 1/2 of our width, i.e. 60 millimeters. Lastly, we have a circle that's centered 80 millimeters above our x-axis, and this is being removed from our shape. The area of our circle is pi r squared, where our radius is 40 millimeters. Thus, we have an area of 5,030 millimeters squared, and our x bar and y bar locations are given as 60 millimeters and 80 millimeters, respectively. To determine our first moment of areas in the x direction, we have to sum all our first moments. That is, we can say MYZ is equal to the sum from I is equal to 1 to 4 of x bar I, AI. Now we're going to take this in order of appearance of our shapes. Our first shape was a rectangle, where our x bar of a rectangle was 60 millimeters, and our area was 9,600 millimeters squared. Next, we're going to consider our triangle. Our triangle had an x-bar of 40 millimeters and an area of 3,600 millimeters squared. Next, we will consider a hemisphere that had an x-bar of 60 millimeters and an area of 5,660 millimeters squared. Lastly, we are going to consider our circle. Now we are removing this. There is a hole within our shape. Thus, there will be no contribution to the moment due to this removed area. Therefore, we are going to subtract the quantity x bar a. That is, we're going to subtract 60 millimeters times 5,030 millimeters squared. And we are left with a value of 758,000 millimeters cubed. Now the distance from our y-axis is going to be given as myz per our total area. That is, x bar is equal to 7,580 millimeters cubed per the sum of our areas, which is 9,600 millimeters squared for a rectangle, 3,600 millimeters squared for a triangle, 5,660 millimeters squared for a hemisphere, and less than 5,030 millimeters squared due to our circle. Therefore, x bar is equal to 54.9 millimeters. Following the same process, just in the y direction, we can calculate the moment m sub zx, and this is equal to the sum from I is equal to 1 to 4 of y bar I, ai. Proceeding in order of appearance, our y bar for our rectangle was 40 millimeters and our area was 9,600 millimeters squared. Next was our triangle. Our y bar was minus 20 millimeters. That's because this was below the x-axis times our area of 3,600 millimeters squared. Plus now, our hemisphere, which had a y bar of 105.5 millimeters times our area of 5,660 millimeters squared, less that of our circle, which had a y bar of 80 millimeters and an area of 5,030 millimeters squared. Thus, m sub zx is equal to 507,000 millimeters cubed. To determine our distance from the x-axis, i.e. y bar, we're going to take m sub zx divided by our total area. Our total area was calculated the same as it was before, and we find y bar to be 36.7 millimeters.